We use random variables to model and examine phenomena, and we can examine them statistically. And one of the things we want to know is where is the center of this distribution? What is the expected value? And the expected value can be calculated as follows. You have a measurable function g from the real numbers to the real numbers, and again, measurable in this case means that it's more or less any reasonable function that you can come up with. And then the expected value is simply some kind of weighted average. How is that? Well, we take any value small x that the random variable can take, and we transform it with the measurable function g, and this g of x value is weighted with the probability mass of the original x. And then we sum over all of them and we get this weighted average of function values. That's the discrete case, and in the continuous case it works almost the same. Again, there's this analogy between summing out and integrating out that is very important, that you should keep in mind. So in the continuous case we integrate out all possible values from -infinity to infinity, and we weight by the density function, and then we get the so-called expected value of g of x. And there's one very important special case, and that's the so-called mean. And in this case the function g of x is simply the identity function x. And so there's a slight difference between the mean and the expected value. The mean is a special case of the expected value. The expected value allows for any measurable transform g. And there are some properties of the expected value that are inherited from properties of the integral. The first one is that if you have a constant function a, then the expected value is simply a. Now, if you multiply a measurable function by a, it's still measurable, and you can pull out the a actually from the integral. You know this from normal integration. And also, if you have two functions f and g, and you apply the expected value to both of them, you can actually apply them individually and then sum up. And these properties that we just talked about, they are usually combined, all of three of them together. They are usually called the linearity of the expected value. So if you read about the linearity of the expected value, these three rules are the ones you have to think of. And there's one more property of the expected value, and it relates to probability measures. And what you do is you take the indicator function of a set. The indicator function of a set is pretty simple. If you have I a of x, it can take exactly two values, namely 1 and 0. And it's 1 if x is in A, and 0 otherwise. And if you take the expected value of such an indicator function and you insert the random variable, then you get out the probability of x being in A. And well, why is that? Maybe it doesn't seem too intuitive to you, but the reason is actually quite simple. Think of A being the whole real line. Then this function I of A is just the constant 1 function. And what you then actually do is that you simply sum over all probability masses, or you integrate over the density. And we know from the properties that we discussed that the result will be 1, and that's the probability of being somewhere on the whole real line. And what you do if you use the indicator function on a smaller set is that you simply weight all points with 1 and that are in the set, and you ignore all the other ones. So you count only the probabilities that are in this set, and then you come up with the probability of the set A. And that's sometimes useful to use. even though it doesn't seem very intuitive right now. Now we've studied the expected value, and the expected value and also the mean as a special case, they can give you a good clue about the location of the distribution on the real line. However, this is not sufficient to characterize distributions. For example, if you have a fair die roll, then the expected value or the mean is 3.5. But now assume that you have an unfair die which only gives you 1s and 6s with equal probability. And if you do the calculations, you will see that this unfair die also has a mean of 3.5. And there is no information in the mean about this being unfair or not. And there is a second measure that we can apply to random variables that helps us characterize the distribution, and that's the variance. And the variance characterizes exactly what I just described in the example, namely how concentrated the random variable is around the mean. In the case of the unfair die roll, we had just 1s and 6s, and they are much further away from the mean than the normal distribution, the fair distribution, which has equal probability also on 2 to 5. And how do we calculate the variance? The variance is itself an expected value, and it's the squared difference from the mean. So what we examine is we take the mean, so the centered location of the random variable x, and we subtract it from the random variable x, the actual outcome. And this means that we center the distribution on 0. And then we take the square, so that we have positive numbers, and take the expected value of this as the variance. And because this first definition is a little hard to calculate, you can apply some analysis to this, and you can actually see that it's the same as the expected value of x squared minus the expected value of x squared. So here's one first example where we have applied a measurable function g to the random variable x. So here we have squared the random variable before we took the expected value. And the variance also has some properties. If you have a constant variable a, then the variance is 0. Why is that? Well, in this first formula here, you just take a minus a, that's 0, and then you square it, it's 0, and then the expected value of 0 is just 0. And also you can have a factor a in front of the random variable, but unfortunately the variance is not linear, and the reason for this is the squaring up here. That's why it's not linear. And if you have a factor of a, you can still pull it out, but you have to square it. So the variance of a times f of x is a squared times the variance of f of x. And sometimes you also talk about the so-called standard deviation. The standard deviation is simply the square root of the variance. The variance is always positive. That's also because you square. If you square, you get positive numbers only, so this expected value also has to be positive, and so has the variance. And now the question is, why do you want to talk about the square root if you can just take the normal variance? Well, due to the squaring, the variance has a different dimension than x. It doesn't have the same unit, for example. And if you want to express something in the domain of the random variable, you have to go back to the standard deviation, because it will have the same unit as the original variable x. And that's the use of the standard deviation. So what have we done so far? We have discussed mean, standard deviation, variance, expected value of a distribution or of a random variable. And that's very useful stuff, but it's also very standard. And now we're going to look at a more sophisticated example of what is possible with the help of distributions and random variables. And this will be the so-called Shannon entropy. The Shannon entropy is named after Claude Shannon, who invented it in 1948 in a very influential paper on information theory, if you want to read more about this stuff. We will just look at the Shannon entropy for a discrete random variable, but it's easy to extend this to any kind of variable, in particular to continuous random variables. So what is the Shannon entropy? The definition is just a special kind of expected value. So what do? You take the negative expected value of the logarithm of the probability mass function. Now, the logarithm of the probability mass function, that's a measurable function. So we haven't violated the definition of the expected value. And what does this thing do? Well, the logarithm of a probability, because the probability is between 0 and 1, so the logarithm of this will be between -infinity for probability 0 and 0 for a probability 1. And now let's look at the extreme cases of this distribution. Let's assume the distribution only has one possible value, and this possible value then of course has a probability of 1. What happens then? Well, this term here, the first term, it becomes a 1, but the second one is a 0. So in this extreme case, the entropy is a total of 0. And now let's look at the other extreme, namely a uniform distribution over n different values. That means each of the n values has a probability of 1 over n. And in this case, you have that the entropy of this random variable x is the following. It's this minus here, minus n times 1 over n. 1 over n is the probability of the random variable taking the particular value. And the logarithm of this probability, that's log 1 over n. And now the n, that's from the sum, and the 1 over n, they cancel out, and you are left with minus log 1 over n. And if you know your logarithm rules, then you can see that this is the logarithm of n. So this is a strictly increasing function. It's increasing slowly, but the more values you have, the higher your entropy is. And so you can get a flavor of what the entropy is measuring. If you only have one value, it's 0. If you have n values and each of them is equally probable, then you get a strictly increasing function. So what it measures is the surprise. How much do you know about the result beforehand? If you know that the result will have a probability of 1, then there's no surprise and the entropy is 0. If all of them are equally likely, then you get a strictly increasing entropy. One example that I found very intriguing in this context is that of Morse code. Morse code actually has a relation to entropy. And to this end, consider the random variable x, and x has the distribution of the letters in the English language. So you know the letter E, for example, is the most frequent one, while there are others like the X, for example, that are much less frequent. And X models this distribution of letters for the English language. Now, the optimal Morse code, it will assign few signals to very frequent letters. So the letter E in Morse code is just one signal, while there are other letters that are much less frequent that take up to 3 signals. And now the fascinating thing is that the entropy of this frequency random variable X, it tells you the expected number of signals that you're going to need to send one letter. And we're talking here about the bits, the signals in the Morse code, and not about ASCII code, because in ASCII code they are all equal, but about the information content of one signal of the Morse code. And we can go even a bit further with this example, but to this end we're going to need the so-called Kullback-Leibler divergence. The Kullback-Leibler divergence takes not one distribution but 2 distributions, 2 probability mass functions P1 and P2, and it measures the so-called relative entropy between P1 and P2. And that's kind of a dissimilarity measure between 2 probability distributions, but not quite. Let's look at it. So the KL divergence, Kullback-Leibler divergence, is defined as another expected value in P1 of the logarithm of P2 over P1. Again, let's look at extreme cases to understand what this formula does. Let's consider the case where P1 is equal to P2. In this case, the ratio in the logarithm evaluates to 1 because they are equal, and then the logarithm is 0. So if they are equal, the KL is 0. Then again, if P1 is much bigger than P2 for some x, then this ratio in the logarithm tends towards 0, and then the logarithm tends towards minus infinity, and the minus infinity cancels out, the minus of the infinity cancels out with the minus in front of the sum. So if they are very dissimilar in a position x, then the KL will have a very high positive value. So a high KL divergence corresponds to a high dissimilarity between P1 and P2. Now that's quite useful. There's only one problem with the Kullback-Leibler divergence. You can already see it from the definition. It's unfortunately not symmetric. So the KL of P1 and P2 is not the same as the KL of P2 and P1. And that's why it's not a measure or a distance measure in the mathematical sense, but it's still quite useful to analyze the difference between 2 distributions. And now we can return to this Morse code example, and now we're going to look at P1 and P2 as the letter frequencies of the English language, that's P1, and the letter frequency of the German language, for example, that's going to be P2. And we know that P1 and P2, they are similar, but they are not equal. For example, in both languages we will know that E is much more frequent than Q, but for example in the English language the letter Y is much more frequent than in the German language, so there is some difference. And now we can return to the Morse code. We have said that the entropy measures the expected number of bits that we need to transmit one letter. Now the KL divergence between these 2 letter frequencies of the 2 languages, it measures the amount of extra bits we need if we use a suboptimal Morse code. So if we use a Morse code that is optimized for the English language, we're gonna need more bits to transmit an average German letter. And that's what the KL divergence is measuring. It measures how much extra bit we're going to need for a German letter. And now we've seen the entropy and the KL divergence, and they are two very good examples to see how powerful this setup of random variables is to analyze phenomena that we observe.